Hello, welcome to today's video where we're going to be looking at solving a system of equations. And you might notice that it's got a heading of matrices. And that's because if you look in most further maths A-level textbooks, that's generally where you'll find this particular topic. But admittedly, in reality, this is a topic that requires you to pull knowledge from a few different areas in maths. And one of those is matrices, but it's just worth pointing out matrices is not the only thing we're going to be doing today. And then the other thing to point out is that this is a topic that's going to take a bit of explanation initially. So to avoid talking you for too long in one big go, I'm going to split it into more than one video, and this will be the part 1 video, and then the part 2 video will follow shortly, I'm sure. So with all that said, what are we actually even trying to do today? We are trying to effectively look at some simultaneous equations, which at first glance might seem a bit of a weird thing to be talking about because you're thinking, we've already dealt with that earlier in further maths A level. We looked at being able to solve even triple simultaneous equations like you've got here, because you could use matrices to do that. But we're not just interested in just solving them. Instead, we're interested in determining the following things. We're interested in knowing the number of solutions this system of equations will have. We're interested in deciding whether they are a consistent or inconsistent system of equations. And lastly, we want to decide what the geometrical configuration of this system of equations is. So those are the three sort of bullet points, the three criteria we're needing to meet. The other thing to point out is that when they ask these questions, sometimes they are a bit unkind with the way they word the question, because they'll make it look very imposing, because these three bullet points will all appear all as one big question, one big paragraph like this, and therefore there's some students who will look at these questions and just think, oh my goodness, how do I do this? Because it looks scary because all these words here. But as long as you're aware it's just these three sort of criteria we're trying to deal with, it's not too bad, because I'm going to be showing you how you can think about each of those criteria in this video. So first of all, actually, let's explain what those three criteria are talking about. The first one to talk about is maybe the most obvious one, numbers of solutions. But you might be thinking, how does that vary? Because if we go back to a simpler time when we were just dealing with two simultaneous equations with two variables in, of course we're aware by now that you can draw a graph and draw lines to represent each of the two simultaneous equations, and then where those two lines intersect is then referring to the number of solutions those simultaneous equations have. So most of the time when you're solving simultaneous equations at Maths A level, at GCSE, whatever, you're getting one solution, and that's because the two lines intersect in one place. However, if you're thinking about it from a graphical standpoint, you might quickly realize that having two lines that intersect in one place is not the only way you could draw two lines. So I'll tell you what, pause the video, have a quick think about what are the other ways we could draw two lines in ways that would affect or change the numbers of solutions we have, so that it's not necessarily just one solution. So have a think about that. And once you've had a thought about that, well, let's reveal what are the other options. Ultimately, other ways you could draw the lines could involve things such as drawing the two lines so that they are parallel. This means they're now no longer intersecting anywhere, so actually in this case, there's no solutions. You wouldn't get asked that at Maths A level unless it was within a sort of discriminant-based question or something like that, because it is a bit weird, because it would almost be like a trick question. Solve them, but you can't solve them. There's no solutions. And then the other option is that actually instead of having one line and then another line separately, we could have the two lines so that they are overlapping. And in which case, actually, it's a bit weird, but it means that technically there are infinite solutions, because every single solution on the original line is therefore a solution to the simultaneous equations. Again, would you get asked that at Maths A level? No, because that would almost seem like a trick question. But therefore you can start to see that the number of solutions we have to simultaneous equations can vary. And therefore that leads me on to the next thing, because you're probably wondering how that works with triple simultaneous equations. Well, to understand that, first we need to have a look at what we're talking about when we talk about simultaneous equations, or equations in general with three variables in. Because equations with two variables you are already aware as being an equation representing a line in 2D. But as soon as we add the third variable in, it's very easy to look at that and think, well, that's still going to be a line, but it's going to be in 3D because we've got 3 variables. But that actually isn't the case. In reality, by introducing that third variable in the format you can see on the screen right now, what you're now dealing with is what we call a plane. Now, we are going to be looking at the idea of planes a bit more in the vectors chapter, but just in case you haven't come across that chapter yet, to explain what a plane is, the best analogy I can give to you is it's almost like an infinite sheet of paper, or for the sake of the demonstration I'm doing right now, you can see that I'm using a mini whiteboard. And the idea is this: basically, in one particular direction, the plane is something that has negligible thickness, just like you can see if we look at this whiteboard from the side. But then in the other directions, 90 degrees to that direction, in those other directions, it's just spreading out forever. So that's why I said hence an infinite sheet of paper, if you will. Now, the reason that's interesting is because then if you play about with this, you can still have this idea of 2 parallel planes, and that, causes no solutions because they're not intersecting anywhere. Or if they're not parallel, then you can start having them intersecting, and therefore that affects the number of solutions you have, etc., etc. Cool. The last thing we need to explain is, what do we mean by the words consistent or inconsistent? Well, luckily it's actually very simple. Ultimately, it boils down to the idea that if we're saying the system of equations is consistent, we are saying there are solutions. I'm not saying exactly how many there are, but there's at least one. It could be 1, 2, 10, an infinite number. All those are examples of the system of equations being consistent. Whereas inconsistent is therefore just quite simply no solutions at all. Okay, now we've explained what all this terminology means. Now we can actually get stuck into actually trying to find out for a particular set of simultaneous equations which of these things they are or are not. And the way of doing this is actually just to do a few sort of checks, if you will. And often in some textbooks, or even me if I'm teaching this to a class, I bring about this idea of this flow diagram. Now, presenting this flow diagram all at once on the screen as I am right now, it looks quite scary, and that's partly why I'm doing this in more than one video. In this video, we're just going to be focusing on this part of the flow diagram, so yeah, don't worry. And each of the parts of the flow diagram is just, looking at individual checks for particular things. So each individual check is really not that bad to do, and it just looks scary because we're presenting it as this one big thing on the screen as we are right now. So to deal with that issue, let's not look at the flow diagram as a whole for the moment. Let's just zoom in and focus on the very first check you need to do, which is you need to look at your equations, and you need to look at the coefficients of the x, y, and z in each of those equations. What you need to do is to check if the coefficients in one equation are just multiples of the same coefficients in another equation in your system of equations. So what do I mean? Well, I mean if, for instance, we had the equations 2x plus y plus 7z, and we could have a number on the end, but that doesn't matter for the moment. And then we could have a second equation, which could be 4x plus 2y plus 14z. In this case, we'll just make the number on the end equal 23 for no apparent reason. What you're looking at is you're looking at the coefficients. So the first equation has coefficients of 2, effectively 1, because we've got one lot of y, and 7. And then if we look at the coefficients in the second equation, we realize they're 4, 2, and 14, which are all double the coefficients of what we have in the first equation. So that is an example of what we're looking for, and this is the scenario where we'd say, yes, this is happening, and we'd go and do some other stuff. Whereas if we had, for instance, 2x plus y plus 7z equals 1, and instead had 6x plus 3y plus 10z equals 34. This would be an example of the coefficients not being a multiple of what's going on in the other equation, because although this first coefficient can be multiplied by 3 to get the 6x in the second equation, and although 1y times by 3 does get you 3y, 7z does not get multiplied by 3 to get 10, so therefore this is what's causing the issue, and so therefore they are not multiples of each other when you're looking at the coefficients. So that's the first check you need to do. Very simple, very quick. You don't need to show any working. It's just like a yes or no sort of thing. Once you've decided that is happening, the next thing you need to then do is then to look at the constant on the end as well, and then decide, is that also the same multiple as the coefficients were? So what I'm talking about are sort of scenarios like this. Let's say we had 2x plus y plus 7z again equals 1. Have we got 4x plus 6y plus 14z equals, I don't know, for instance, 2? Or could we have another scenario where we've got 2x plus y plus 7z equals 1 versus, sorry, it's a very bad 7, versus, let's say we've got 10x plus 5y plus 35z equals 23. Now, the difference between these two scenarios is in this first scenario, we notice we're multiplying all the coefficients by 2 on the left-hand side to get the equation below, but we're also multiplying the constant on the end by 2. So because we're literally multiplying everything in the equation by the same number, then we've got a sort of common multiple across both equations. Whereas in this second set of equations, we're multiplying the coefficients by 5 to get from the first equation to the second equation, but the number on the end, we're multiplying by 23. That means we're not multiplying by the same thing. We're multiplying, we've got different multiples to the coefficients. That is what you need to be checking for, because if you are multiplying by different coefficients, this is an example of parallel planes. If the coefficients are a multiple but the constant in the end is different, whereas if we have literally the entire equation multiplied by the same number, both the left and the right hand side, then literally these are the same planes. So that's something to be aware of, because once you've decided if that's the case, what you need to be aware of is the moment there are any planes that are parallel, you instantly know there are no solutions. And you can realize that by thinking about it, you know, with the idea of the two sheets of paper. If they're parallel to each other, they're never going to intersect. There's not going to be any solutions. And therefore, cycling back to what we said earlier, that is therefore what we call inconsistent. Inconsistent means no solutions. And then a geometrical configuration is just, well, you describing what is going on. How many planes are parallel or not? If just 2 of the 3 are parallel, then say 2 out of the 3 are parallel. If all 3 of them are parallel to each other, then say that. But if none of them are parallel, then instead we are aware that some of them are literally the same plane, so therefore they're overlapping everywhere. And what that means is if 2 of the planes are overlapping everywhere, there are infinite solutions. Therefore we say it's consistent because there are solutions of some variety, and again you just describe in terms of the geometrical configuration literally directly what's going on. Worth pointing out, the parallel planes part is the bit that's got priority. So the moment there are any planes that are parallel, you know you're in this section of the flow diagram. So let's look at an example of that going on in the context of a system with 3 equations in. If we have the same sort of equations we had before on the previous slide, 2x plus y plus 7z equals 1, and then the other equation was 4x plus 2y plus 14z equals 2, and then the last equation we had was 10x plus 5y plus 35z, I think it was equal to 23. What that means is we know that these 2 planes are parallel already, but we also know that these 2 planes are identical. So that means we got the situation of parallel and identical both happening at the same time, but therefore the thing that takes priority is because any of the planes are parallel to each other and not identical, that's the thing that decides therefore that we are in this particular part of the flow diagram, and therefore we will say that there are no solutions, it's inconsistent, And for the geometrical configuration, you'd just be describing literally what we just identified, i.e. that there is two planes that are identical to each other with a third that's technically parallel to both of those other planes. Cool. So that's just the first check you need to do. It's really simple. You almost don't really need to do any calculations. You can kind of just stare at the equations and kind of decide whether they are parallel or not, or if any of them are the same in that regard. But what happens if none of them are parallel? Well, there are other checks we need to do instead. And the next check we need to do is to think back to what we were doing last time we were solving simultaneous equations using matrices, because we were sometimes solving the simultaneous equations using inverse matrices. And of course, you know, in order to be able to have an inverse matrix, you need to be able to do 1 over the determinant of that matrix. But that's a problem if the determinant of that matrix equals 0. If the determinant of a matrix equals 0, what we call a singular matrix, it has no inverse matrix. So that's a yes or no sort of check, which also then therefore tells you yes or no about whether you can or can't solve the simultaneous equations in the way that we were doing before to get a single individual unique solution. So therefore, if the determinant of the matrix of the coefficients is not equal to 0, we say the matrix does have an inverse, therefore there is a unique solution. We can say it's consistent because there are solutions. It's one solution, but therefore it's still there are solutions. And then just geometrically what's going on is the three planes are just intersecting at a particular point. And an analogy for that would be if you're in a room. The room I'm assuming you're in is probably a cuboid shape, and therefore if you look in any corner of the room, you'll see there's the two walls and maybe either the ceiling or the floor all come into contact at that one point where the corner is, and therefore that is an example of three planes intersecting at one point. So a very easy check to do, just work out the determinant of the coefficients. Is it 0, yes or no? If the determinant is equal to 0, well, that's something we'll leave for the part 2 video. So therefore, for the moment, we'll move on to doing some examples. Both of these are just quick checks you can just do. So it's just about doing them and getting on with it and then making the relevant conclusion from that. So looking at example 1, we first do the check for looking if any of the coefficients in one of the equations are just a multiple of the coefficients in another equation. So, for instance, we compare the first two equations. We very quickly realize that although you need to multiply the x coefficient by 9 to get from the first equation to the second equation, you need to multiply the y coefficients by -1. And so therefore there isn't a single common multiple we're multiplying all of the coefficients in the first equation by to get the coefficients in the second equation, so they are definitely not parallel or the same. But then if you look at the first and the third equation, you notice that 1 times by 5 is 5, 2 multiplied by 5 is 10, and 3 multiplied by 5 is 15. So they do have a common multiple of the coefficients. So then you need to check the numbers on the end. Well, if we need to multiply the coefficients by 5, what do we need to multiply the numbers on the end by? Well, the answer is not 5. It's 9 over 4. And so therefore, because the constant on the end is not multiplied by the same number as the coefficients, we can say the first and the third plane are parallel. That's important because it instantly means we know that there are no solutions because there are parallel planes at all, and therefore it is inconsistent. So really, that is as easy as it is. That's why we do that check first, just because it's a very quick thing to do. Second equation, or second example, I should say, we're now going to again check, are any of them parallel? The first and the second, definitely not parallel. First and the third, definitely not parallel, and then also the second and the third, they're also definitely not parallel to each other because the coefficients are not multiples of each other. So then the next thing we need to do is calculate the determinant of the coefficients. So we need to work out the determinant of 2, 1, minus 1, 1, minus 5, 4, 42, minus 1, minus 3. And you're welcome to use the calculator to work out the determinant. If you do, you will get an answer of 0. But wait a minute, that's the area of the flow diagram we haven't dealt with yet. So for the moment, this is a mystery in terms of what's going to happen. We know there's not unique solutions at the very least, and we know they're not parallel, but therefore look at part 2 to see what to do with this beyond this stage. Cool. Then moving on to example 3, the exact same checks again, checking if any of the equations have coefficients that are multiples of each other. So therefore, we compare the first and the second. They're not parallel. First and the third, they're not parallel. Second and third, they're not parallel either. So then we move on to calculating the determinant. So we're going to do the determinant of 3, 2, 5, minus 1, 6, 2, 2 minus 4, 9. And if you were to work out what that is as a determinant, it comes to apparently 172, assuming I've typed that into the calculator correctly. That's important because that's not equal to 0. So instantly, therefore, we know it is possible to find an inverse matrix. Therefore, there is a unique solution. We know that there is, well, the system of equations is consistent. And we also know that that involves, therefore, 3 planes intersecting at one point. Cool. So there you go. Really, actually quite easy to do in terms of these steps. We, as I already said, will look at in part 2 how to deal with the situations where the determinant does come to 0, assuming you have already checked whether any of the planes are parallel or not. Brilliant. So I'll see you in part 2. The link to that video is appearing on the screen right now, if the video has been uploaded yet, and therefore I'll see you in that video. Goodbye.